our last talk, which is given by Marcio Pereira, and it's about bridging the gap between OpenMP and cloud computing. Please.
Thank you. Good afternoon. Well, of course, I'm not Hervé, I'm Marcio Pereira. Hervé is the main collaborator in the work about OmpCloud, bridging the gap between OpenMP and cloud computing. And I'm here to present it. So, anything stupid I said is mine, don't blame my colleagues. Okay. A bit of background. Both me and Hervé are postdoctoral researchers, work at Unicamp in Brazil, under the supervision of the professor Guido Araujo. And the main lines of our research are focused on compiling technologies for thread level speculation, for loops, loop tiling, vectorization, cloud parallelization techniques, and so on, like parallel program models, heterogeneous computers, etc. Oh, my current work that I will present in IWAMP, an open source LLVM CLang compiler framework that implements the recently released OpenMP Accelerator program model. Our compiler automatically converts OpenMP annotated loops into OpenCL or Spear kernels, while provide a set of polyhedral techniques based on optimization, like tiling and vectorization. These kernels result from the compilation process can be executed on OpenCL Spear compatible accelerator device. And to the best of our knowledge, this is the first implementation of OpenMP accelerator model to provide a source to target OpenCL conversion, not source to source. Let me start the topic, today's topic. Parallelizing loops is a well-known research problem that has been extensively studied. Some of the approaches to this problem use vectorization, data arrangement, and the loop transformation to improve program performance. On the other hand, the combination of large data center clusters and MapReduce based techniques like those found in internet search engines has opened up opportunities for cloud-based parallelization, which could eventually be seen as new computing resource. We have several cloud providers like Amazon Web Services, Microsoft Azure, as well large data center with massively parallel processing capabilities and the flexible usage. So, the cloud can be seen as a solution, or maybe the ultimate solution for social media and also useful for other domains like IoT. But how to program the cloud? This is an important question. So we see in the left column the application domain, and in the right column the model widely used. For small applications, use Python or in your language, plus the SDK provided for the cloud providers. It's easy to learn, easy to use. On the other hand, big data use MapReduce or Spark with high level of fault tolerance. It's a high level language and fault tolerance. And high performance compute use a low level program, very efficient MPI. But how about something in between these models? On the other hand, are you a program expert? Sorry. Writing parallel program is not so natural, and integrating cloud in your application may require to interface different program languages due to the nature of the hybrid execution model. So, let's make it simple. As you know, OpenMP is a well-known API for developing parallel applications. This is a directive-based program made to be simple and no need to rewrite the code, but it assumes a shared memory architecture. So you just put a program in the code that you have to parallelize. But from OpenMP 4.0 and 4.5, this new OpenMP accelerated model was designed to programming accelerators. But it was designed keeping in mind that the accelerators are connected locally in the host target architecture model. In this example, the matrix multiplication, we indicate the target device this code is executing the target device GPU, and the offloading the data, send it to GPU A and B, and get the result in the matrix C. So, let's be brave. To address this issue, this work integrates OpenMP directive, cloud-based MapReduce Spark nodes, and remote communication management into a single OpenMP offloading device, which can be seen by the program as available in its local computer. This is only a modification for the programmer, point of view of programmer. To achieve this program just indicates this new device. So OpenMP plus cloud is equal new OmpCloud cloud. It's a new development environment for cloud offloading that we call OpenMP Cloud. It's open source. It's available on the GitHub. It's relying on a custom LLVM for a host to generate code for a host device, and on Apache Spark for target device. From a program point of view, just the program describe the application use OpenMP, compile it with our custom CLang, instantiate a Spark cluster in your favorite cloud provider, example Amazon Web Service, configure the OmpCloud runtime with the credentials for accessing the cluster in the cloud, and run the application. In a graphic model, this is the application. So first the program configures the credentials of a Spark cluster previously deployed on the cluster infrastructure. Then the program is then started by the programmer in its local machine and runs until OpenMP annotate code fragment is reached. So a method is then called to initialize the cloud device. Note that the offloading is done dynamically. So if the cloud is not available, the computation is performed locally. Okay? Then the runtime sends the input data required by the kernel as binary files to a cloud storage device. After all the input data has transmitted, send it to the storage, the drive reads the input data from the cloud file, compress it, and broadcast to the work nodes to distribute the loop iteration across the Spark work nodes, which are in charge to the computations. Next, work nodes run the mapping function that computes the loop body in parallel, and the output of the loop is then compressed and collected through a reduce operation and stored in the cloud storage. And finally, the data is transmitted back to the local code, which then continues the execution on local machine. So the model Here we have the fact binary generated by LLVM, which contains host and target codes. While the host code combines the main function and the target codes are such code for CUDA code, for example, for GPU, in the same binary. Our solution requires an additional file to be generated. This code is describing the Spark code that use the Spark job, and they compile to jar binary. The number 2, target agnostic offloading wrapper, is responsible for detection of the available devices, the creation of the device's data environments, the execution of the right offloading function according to device type. So you have also the cloud plugin. The target specific offload plugins performs the direct iteration with the device according to the architecture, and provides services such as initialization and transmission of input or output data. In our case, the cloud-specific plugin used to initialize the cluster, transmit the offload data through the cloud, and submit the Spark jobs. There are cloud configuration file here. This is the major difference between other solutions. And when you use the cloud to offload computing, they compare the cloud device cannot detect it automatically, like I said, since they are not physically hosted at the local computer. So the user has to provide an authentication information and to the current application. So the plugin reads at runtime the configuration file to properly set up the cloud device and to avoid the need to recompile the binary. The login information, the configuration file also contains the address of the Spark driver, as well as the address of the cloud file storage. So, no need to recompile your application. The code is portable for all Spark-based cloud devices. Only change the configuration file. This allows an easy portability over existing cloud service, because this is implemented as a modular infrastructure, where the communication with the cloud to be customized for each existing cloud service by talking into the specifics, for example, storage service, security mechanism, etc. For now, our plugin supports computation offloads for the Amazon Elastic Computer Cloud, EC2. We also support data offload for HDFS and Amazon Simple Storage Service, S3. This can be easily extended to support other commercial clouds, services like Microsoft Azure Cloud, Google Cloud, etc. Another topic, important topic. One central issue in distributed parallel execution models is to enable data partitioning mechanisms that assign a specific data block to the worker nodes. By doing this, program consider benefit from locality, thus reducing the overhead of moving data around the interconnection networks. Automatically data partition is a hard task which cannot typically be achieved solely by the compiler or runtime. In most applications, the programming knowledge is essential to enable an efficient data allocation. Unfortunately, the OpenMP standard does not have directive specific design for data partitioning within offloaded regions. So let it make it possible. We extended the use of OpenMP target data map directive so as to allow the programmer to express the data distribution to the Cloud Spark nodes. No syntax modification was required since the how can I say this construction inside another programmer is undefined behavior by the current OmpMP specification. So you use that to indicate after the to from specify of the map directive to the first element of the partition data block, followed by column under the last element, the first element under by column for the last element of the corresponding block. In this example, we are partitioning the matrix A to distribute according to the index and to compute the parts of matrix C. Not that the Bay matrix are not partitioned. So if you look at this model, first we read inputs A and B from the cloud storage, then broadcast and partition B, generate the set of all values taken by the loop index, and distribute A in the slice A and the E, the index, corresponding index. Map loop body function to take values of the loop index, then send back of parts of C, computed, reconstruct the final version of C, and write C to the cloud storage. This is a small pseudocode for this example. Here's the read inputs for array. Generate distributed list using RDD is a Spark runtime data structure called the resilient distributed data set. Partition data and distribute loop iterations using GNI loop body. Reconstruct the output and write back the result. What the result back? Okay. Another important point is optimize the granularity. When the number of iterations is much larger than the number of cores, an overhead is possible due to the great number of GNI calls. So our strategy is to apply tiny optimization into the loop with block size defined in runtime by the number of the cores. So this user partition is adjusted. Okay. We did a lot of experiments. We performed a set of experiments using a simple laptop like this and the Amazon Web Service Data Center. Here, EC2 means Amazon Elastic Computer Cloud. And using a set of well-known benchmarks like Polybench, Parboil, Rodina, etc. Here, I will show you one example of the matrix multiplication. This case to the using two matrix for 1 GB of floating point. A sparse matrix and a dense matrix. So, in comparing time, the execution time for sequential for this matrix is a 3.5 hours, and in 256 cores we have 3 to 8 minus 3 to sparse matrix, 8 minus 2 dense matrix. So you note that we have an increased speed up from 27 times to 68 times on 256 cores. Another point important point is the communication overhead is almost constant, but of course the data type matter. We observe that the sparse matrix, the communication overhead is less than dense matrix because the compression, sorry. But it almost constant independent of the number of the cores it's expected, the cores that run the application. Of course, we have limitation of this model. The code regions offload to the cloud. Today we support parallel for with nested loops, reduction clause. Do not support atomic, flush, bury, critical, or master. And we'll plan to support blocks of sequential code parallel for inside a sequential loop. Another thing, cluster program sometimes is not adapted. Offloading to clusters not adapted. But you don't need to run only in local computer because host-target communications sometimes are expensive. So you can run the application direct from the Spark drive. Connect with SSH, transfer your application, configure OmpCloud runtime, like said before, and run it. Communication between the binary and Spark are handled seamless using local file. Easy way to program a cluster from C, C++. Okay? So my conclusion is simple parallel programming model, like C, C++, and OpenMP directive. No need to rewrite your code. OpenMP addressed the problem of load computation to cloud infrastructure so as to benefit from a quasi-unlimited parallel processing capability. In order to ease the utilization of the cloud, we designed a runtime that offloads the maps and schedule computation automatically. Our approach allows portability over commercial cloud and service and provide private clouds. Indeed, by using a configuration file, our runtime is able to easily switch from one cloud infrastructure to another without recompiling the binary. And the communication with the cloud storage service and the execution with the Spark cluster is handled automatically according to the given to the configuration. The experiments demonstrate the viability of this solution and promise performance. And the future works is to experiment machine learning, face recognition, and blend the rendering to cluster. I think this is I have to talk. So thank you. Questions?
Any questions?
I try to.
Yeah, for your future work, how do you expect the performance to compare with other? You mentioned at the beginning Python and MapReduce. I know the programming context is different, but like in terms of
Yes, I understand your question. Python is easy to learn and to use with this infrastructure. But I think this, of course, I talk about in the name of the Hervé, not mine, but I think this solution brings the C, C++ developed for the cloud. Because today, programming with this language is quite difficult in this. But I have no information to do for you if this is more efficient or no compared with the Python. Because Python is, I think, is use the libraries, pre-compiled and very optimized in the cloud. Python is only the interface. I think, I don't know. I'm not sure about.
So probably this is a multi-part question, depending on the first one. So did I understand correctly that you're using Java as the execution environment of the cloud?
Yeah, Scala.
Okay, so it's still running on my JVM. And then the second part of my question would be, did you think about using Granularity to actually call into more efficient native code instead of executing?
I apologize, but I don't know exactly. Yes. This question I need Hervé to. I recommend you to send an email for Hervé, because this is their project, and this question I have no answer to that. Sorry.
Thanks again.
Okay.